Ever wonder how your phone knows which way you're holding it? Or how a thermostat gets the temperature just right? I mean, that's all real-world, smooth, analog stuff. But our computers, our devices, they only speak digital, just ones and zeros. So how in the world do they bridge that gap? It's all thanks to this tiny, invisible translator, and we're about to see exactly how it pulls it off.
So here's the game plan. First, we'll get into the two different languages our world and our computers are speaking. Then we're going to meet the amazing little component that acts as the translator. We'll look at how it can go for speed or for crazy precision, how it can prep a signal before it gets translated, and then finally we'll follow a signal's entire journey from the real world straight into the digital brain of a machine.
All right, first things first, we have to understand the core problem. You see, everything we experience, sound, light, heat, it's all analog. But the gadgets we use to measure all that stuff, they're digital. And these two, well, they just don't naturally speak the same language.
Check this out. On the left, you've got your analog signal. Think of it like a ramp. It's smooth, it's continuous, and there are literally infinite points all along the way. But on the right, that's a digital signal. It's a staircase. You can only be on one specific step at a time, nothing in between. That's the language of computers, and our job is to somehow turn that smooth ramp into a series of steps.
So that brings us to the big question, right? How does a machine that only gets these chunky, separate steps make any sense of a world that's all about smooth, continuous flow?
Well, the answer is hiding inside this tiny but absolutely crucial component that acts like an incredibly fast and accurate interpreter. So let's meet the hero of our story.
It's called an analog to digital converter, or ADC for short, and what it does is pretty amazing. It takes a continuous analog signal, say the changing voltage from a temperature sensor, and it just slices it up into a series of digital values. It's the essential bridge that lets our devices actually understand what's going on around them.
So how does it actually work? Well, it's kind of like a three-step dance. First, it picks which signal it's going to listen to, like a DJ choosing the next track. Second, it measures the voltage of that signal at one specific instant. And third, it turns that measurement into a digital number and stores it, all ready for the computer to use.
Okay, but here's the thing. Not all translations are the same. Sometimes you just need a quick, good enough version, for a simple temperature sensor in your house. And that's where 8-bit conversion comes in.
So, with 8 bits of data, the ADC has a vocabulary of 256 words it can use to describe that analog signal. It's like having a ruler with 256 marks on it. Sure, it's not perfectly precise, but for a lot of things, like a basic light sensor, it's totally fine. More than enough, actually.
And here's a typical 8-bit setup in action. See, as we turn the dial, the voltage changes. The ADC inside that microcontroller reads the change, converts it to a number between 0 and 255, and bam, it shows up on the screen. Simple, fast, and it just works.
But what if good enough just isn't good enough? What if you're not just measuring room temperature, but the super subtle changes in a medical device? What if you need extreme precision? For that, we're going to need a few more bits.
Okay, let's level up to 10-bit conversion. Now get this. Just by adding 2 more bits, just 2, we leap from 256 steps to a whopping 1,024 steps. That's like going from a kind of blurry photo to a super high-resolution image. Suddenly, you can see all the tiny little details in the analog signal.
At first glance, this 10-bit circuit might not look all that different, but to get that extra precision, everything has to be way more stable and accurate. It's like building a high-performance race car. Every single part has to be absolutely top-notch.
So really, it all comes down to a trade-off. 8-bit is the sprinter. It's fast, it's efficient, and it's perfect for most everyday jobs. 10-bit, on the other hand, is the marathon runner. It's a bit slower, but it's got that incredible precision you absolutely need for those specialized, high-stakes measurements.
But hold on, there's a catch. You can't just feed any old signal into an ADC and expect it to work. Sometimes the signal is way too weak, or it's noisy, and needs to be prepared or conditioned before it's ready for its digital debut.
And for that job, engineers have this awesome secret weapon, the operational amplifier, or op-amp for short. You can think of it like a personal trainer for your signal. It can bulk it up, slim it down, or even combine it with other signals to create the perfect input for the ADC.
Whoa, okay, I know what you're thinking. This looks complicated. But
Don't worry about all the little details. What you're seeing here is just a demonstration of how versatile the op-amp is. Each one of these little sections is like a different workout routine for a signal, getting it in perfect shape before it heads over to the ADC.
So, what can this little Swiss Army knife actually do? Well, it can act like a megaphone and amplify a really weak signal. It can be a bodyguard protecting a signal from outside interference. It can even be a mathematician, adding or subtracting signals to give the ADC exactly what it needs to see.
Okay, we've met all the players. We've got the signal, the personal trainer, and the translator. Now, let's follow a signal on its epic journey, from just a flicker of light in the real world to a solid piece of data in the digital one.
It all kicks off with a physical event, maybe a sound wave hitting a microphone. Then the amp jumps in and cleans up that signal, getting it ready for translation. Next, the ADC takes a super fast snapshot of the signal, converting it into a digital number. And just like that, the microcontroller has the data it needs to, say, start recording your voice.
And this isn't some abstract theory, you know? This is happening right now, literally trillions of times every single second, all around you. It's the invisible heartbeat of our modern world, allowing your phone, your car, your smartwatch, everything to sense, understand, and react to the world around it.
And that kind of leaves us with a fascinating thought. As our sensors get even more sensitive and our processors get even more powerful, this bridge between the analog and digital worlds just becomes more and more critical. So the real question is, what new senses are we going to give our machines? What will we teach them to feel, see, or hear next? All right, that's it for this deep dive into how our digital world makes sense of ours. If you found this interesting, definitely make sure you're subscribed for more explainers like this. Thanks for watching.